Hello, everyone. This is Gary Klein with Gary Klein and Associates. I'll be the moderator for our session today. We're going to be talking about hot water distribution systems, losses and design. And we have two speakers, Christoph Lohr and Evan Green. Christoph is an engineer with IATMO and Evan is an engineer with Ecotope. They both spend a lot of time looking at hot water distribution systems. So before we get started, there's a few housekeeping things we have to cover. First and foremost, thank you to all of our sponsors and ACEEE ally members for their support of the Hot Water Forum and ACEEE. Second point, use the chat box on the right-hand side of your screen to ask questions of the presenters. As moderator, I'll gather all the questions and share for the presenters to answer once all the presentations are complete. If we don't get to your question during the session, please join us for 20 minutes of chat or discussion on the Zoom platform immediately following this session. The Zoom link is posted on the audience screen at the very bottom. Please refrain from using the chat for any dialogue other than asking questions. I have two kinds of questions. One are clarifying questions, which we'll do our best to get the speakers to answer close to real time. And the other are exploratory questions, which we'll hold till the end and for the Zoom meeting. Be sure to check out the tabs on the left-hand side of the app. From there, you can network with attendees and program participants, visit sponsor pages, and engage in our game to possibly win a free registration to the 2023 Hot Water Forum in Mission Hills, California. The resources section includes the program and a list of attendees for downloading. Lastly, we ask everyone to please help our planning of future hot water forums by completing the conference evaluation. Anyone who completes the evaluation and includes a testimonial will receive a $25 discount off of the 2023 Hot Water Forum registration. All presentations will be available for on-demand viewing to registered attendees on the Socio platform within a few days and will remain available for viewing until May. Presenter slides can be found on their page in the program participants section. Let's see. There we go. We've got all our speakers. So our first speaker is going to be, I think it's Christoph. So you're up.
Excellent. Can you see my presentation? I went ahead and shared screen. Excellent. I see that now up there. Well, first off, Gary, thanks for the introduction. As Gary had mentioned, my name is Christoph Lohr. I am Vice President of Strategic Initiatives with IATMO. But my background is as a plumbing engineer. I spent over a decade doing plumbing engineering design within the built environment, predominantly in healthcare, but did my fair share of sports stadiums, high-rise buildings, apartment complexes, a little bit of residential, along with higher education, education facilities, and basically everything under the sun. So I felt very fortunate to have that background in a lot of commercial buildings. My talk today is going to be focusing predominantly on some of the sizing criteria, and my fellow speaker, Evan, is also going to be touching on this, and hopefully you'll see some common threads between our two presentations in terms of the approach that really I think could be described as sort of the minimum engineering practice that should be taken in terms of sizing hot water return systems. And there's some really important key reasons to go ahead and focus on hot water return systems. Really, I would make the argument that hot water return systems are a very critical, if not one of the most critical systems in a plumbing system within the built environment. Many of you probably have heard, I was here fortunate last year to be a speaker for you all, kind of talking about hot water temperatures and Legionella. Really when it comes to hot water systems, most of the Legionella positivity cases stem from the domestic hot water system. That seems to be the leading sort of the critical junction point within plumbing potable water systems in terms of Legionella. And what's interesting is when you look at hot water return systems specifically, there's a huge opportunity, not just from an economic standpoint and improving how systems are built and making them more efficient, but also in terms of reducing costs of construction while minimizing the potential negatives of public health and safety. And a really enlightening story is a facility that I was doing some work on a number of years ago, brand new hospital in downtown New York City that I think it was like a 20-story hospital, had multiple pressure zones, multiple hot water, well, had a singular hot water supply system. And the hospital, they had a water management program. They had supplemental disinfection. And within a few weeks of the hospital opening, they had Legionella positivity in their facility. In terms of the hot water system was testing positive. Fortunately, they didn't have any cases, but they were really struggling to try to figure out what the cause was. Well, after a lot of troubleshooting, in which everything under the sun was blamed, what was going to be determined what the root of the problem was the hot water return system was never balanced. The hot water return system was out of whack, which led to stagnant conditions all throughout the facility. And in my conversations and giving a version of this presentation, which typically is 1 to 2 hours, I'm condensing a lot of material into a very short amount of time. In those conversations with engineers across the country, there's a common thread that is hot water return systems are not being balanced. Now, on top of that, what I've come to find out in giving that presentation is that not only is it a balancing problem, so on the commissioning side, but it's also that in some cases there's engineering issues, and in some other issues there's retrofit issues as well. So this thought process of hot water return systems it expands to well beyond just the construction side. So what are some of the issues? Well, we have the manual balancing valves not being balanced. I'm going to get my laser pointer here. We have manual balancing valves not being balanced. We have a hot water return pump. Sometimes that is undersized. We have hot water supply via the Hunter's curve in lieu of other design methodologies. And we have, in more cases than not, one of the biggest issues is a 30 BTU per hour assumption for the hot water return system in terms of BTU loss. And that is a really bad assumption. And I'll touch on that during our presentation here today. One of the other issues, though, is a lot of times, especially in hospitals, as projects are retrofitted, you have future loops are either wrongly located, so you have them tying in upstream of a balancing valve, or they're not even part of the hot water return evaluation as a whole. And so the pumps end up becoming undersized. So a whole host of issues can occur as a result of improper design, but then you compound that with the installation issues. Actually, installation tends to not be the issue, but sometimes it is. But the commissioning and balancing that doesn't happen, and then owners not going back and doing a whole system evaluation, or engineers not going back and doing a whole system evaluation during reconstruction or during renovation or addition work. It just compounds the issue. All right, so when we talk about the methodology, and that's what I'm going to focus the bulk of my presentation on here. In essence, we have 4 equations. So you can see here the 4 equations. One is dealing with the assumption of conduction, heat transfer from the pipe through the insulation to the ambient air. The other one is the heat transfer of the fluid as it flows. Equation 3 is for velocity, determining the velocity. And the 4th equation is head loss. Again, in order to properly size a pump, there's 2 criteria we need to know: the flow rate and the head. Now, when we're designing hot water return systems, we are assuming a closed state condition. So what do I mean by that? So normally plumbing systems, unlike hydronic systems, hot water return systems, domestic hot water return systems, they can be either open or closed. Hydronic systems are much easier because they're always closed and you always have 100% of the flow returning. Domestic hot water systems don't operate that way. All we're worried about is temperature maintenance. In essence, trying to get that heat source as close to the plumbing fixture as possible. So these are the 4 equations that we use, and we're utilizing these 4 equations under the assumption that the hot water return system is in a closed state. That is, none of the plumbing fixtures are open. So that way, when a fixture is open, you have that hot water demand there. Well, one of the things you'll notice is I have sort of a number of the criteria here selected in blue and green. The blue represents actually one variable, which is the diameter of the hot water return system. Again, the hot water return system can be smaller than the hot water supply system because we're not returning 100% of the flow. Typically, we're just returning a portion of the flow. The variables that are in green are the other 4 variables that we have to determine based on variances in pipe size and everything else. So we have the flow rate itself that's needed to maintain that temperature. We have the temperature differential from the fluid as it goes into the hot water return system or into the hot water system and then comes out of the hot water return system. And then we also have our fluid velocity, which is a concern based on pipe material. And finally, our head loss. The head loss and flow rate are the two criteria that are the most key in sizing the pump. And I apologize for my cat going crazy in the background. I don't know what's going on with her today. Finally, again, the diameter, which impacts the area, the internal pipe cross-section, those are highlighted there in cyan. That's one variable. But what you'll notice is even if you combine all those blue into one variable, we have 5 variables and 4 equations. We have too many variables. You can't solve based on trying to solve one equation by using the other. So what do we have to do? We have to utilize a methodology called Hardy-Cross. And this is not something that is, what's interesting to me is this is something that when I've brought this up in engineering seminars, many engineers look at me as if the first time they've heard it. But it is not an unused terminology. Actually, if you look at the Michael Lindberg Professional Engineering Reference Manual, which is probably the most used manual in preparation to take the professional engineering exam, it's referenced right in that document. And this quote here: network flows and multi-loop systems cannot be determined by any closed form equation. Again, using one equation to solve another. Most real-world problems, such as a hot water return system involving multi-loop systems, are analyzed on a computer. Computer programs are based on the Hardy-Cross method, which can be performed manually when there are only a few loops. In this method, flows in all of the branches are first assumed, and adjustments are made in consecutive iterations to the assumed flow. So again, I'm not making this up. Now, this corresponds, what's interesting for me is this corresponds to a class that I had in college called Energy Conversion Design. And I graduated from the Virginia Military Institute in 2008, and it was part of my senior coursework, required coursework at the time. And what's been interesting to me as I've mentored young engineers and given this presentation is it seems much of people that design plumbing engineering, hot water return systems, whether plumbing engineers or general mechanical engineers that do both HVAC or plumbing, most people haven't had this class or didn't have this class as part of their coursework. I had a whole semester of this class covering Hardy-Cross. And so there's been, I think a lot of the issues we see on hot water return systems are a result of a lack of education on this subject. All right, so the first one that I mentioned before is 30 BTU per hour per lineal foot is a really bad assumption and is one that's being done in the industry currently that should be done away with. Why is that? Well, when you look at and you actually calculate out heat transfer rate per lineal foot, and you base it off of fluid temperature and different pipe sizes varying due to insulation thicknesses, what you'll notice is that 30 BTU, you don't even get close to that value until you get either a 4-inch pipe at 160 degrees Fahrenheit or a 6-inch pipe at 130 degrees Fahrenheit. Most of this piping in a hot water system tends to be 2 inches or smaller in most cases, especially if you're utilizing the water demand calculator. You can get the smaller pipe sizing. So in essence, what has happened is, especially in some facilities where this 30 BTU per hour per lineal foot has been used, is the hot water return system dictates the supply sizing. And I've seen this happen and play out in a small 50,000 square foot hospital where, because the hot water return system was so complex, or the hot water system was so complex, the hot water return system actually drove the sizing of the hot water supply system. They ended up with larger mains as a result. What a waste of materials, waste of energy, waste of pumping costs. Again, the bigger increases you have in flow, the more pump energy you'll use because of the pump affinity laws. So really getting the right assumption for a BTU per hour per lineal foot heat loss is step one. Again, I made some assumptions on insulation and temperature. That's part of the slides there. And these charts will hopefully be in the ASPE Legionella Design Guide, and this methodology will hopefully be captured in the ASPE Legionella Design Guide that hopefully be released for public review here at some point this year. All right, the second equation is our flow rate and temperature drop through a given length of pipe. So again, we have our conductive heat losses. That's our T1, T2. That we've determined that based on the charts before. But those two heat losses should be about the same. And so when we have that fluid flow going from T3 to T4, we have a certain flow rate and a temperature drop there. So we know, based on the water heater, let's say it's set for 140, we know what our T3 is. To figure out what T4 is, we have to make an assumption, or we have to make a calculation, not an assumption, but we have to have a calculation based on an assumed flow rate. And typically flow rate is the starting assumption point. All right. So the second, another one of the variables that we have to be mindful of is velocity limitations. So again, remembering velocity was one of those 4 equations that I had indicated. For copper piping, per the Copper Development Association, for hot water systems up to 140 degrees Fahrenheit, a maximum of 5 feet per second is the maximum velocity. In systems where you exceed 140, which is happening more and more often because of Legionella concerns, many systems now are being designed for 160 degree distribution in the mains and main branches. You have to slow that velocity down to 2 to 3 feet per second. Again, otherwise you have an increase in erosion corrosion concerns of the piping material. So there's a give and take here. We can't just make the assumption of all these systems being the same. And this is something often that is not considered. And so again, we need to be mindful of some of these assumptions and where they stem from. All right, so let's say we had this system. We had this system here that was all 1-inch type L copper. We had 400 lineal feet. We were utilizing a 2015 energy code, and we had 140 degree Fahrenheit hot water system, right? So, if we wanted to find the flow rate, the temperature, the velocity, and head loss, we'd have to make some kind of assumption of flow rate to begin with. So let's say we assumed 1 GPM was flowing through here in a closed state condition. Utilizing, the series of calculations here, we'd end up with a 7.25 degree Fahrenheit temperature loss, a maximum velocity through that 1-inch type L copper of 0.41 feet per second, and a pressure drop of 4.2 PSI. Now, if we were to increase that flow rate because we wanted to reduce that temperature drop, let's say we didn't want that high of a temperature drop. We wanted to keep it as close as possible. And we increased that GPM to 5 GPM and we ran a second iteration with all those calculations, we would end up with a 1.45 degree Fahrenheit temperature drop for that 5 GPM, a 2 feet per second maximum velocity, and 9.2 PSI pressure drop. All right. Any questions on that so far? Gary, anything that has come in through the chat? I'm not seeing anything, so I'll go ahead and move on. So the next thing we have to keep in mind, though, that's a very simple example, and most domestic hot water systems are not that simple. But what we want to do is go back and sort of remember some of our basics in terms of piping system and fluid dynamics within a multi-loop system. So the first is when we have pipes in series. So let's say we have pipe A that is, say half the pipe diameter of B. So and we have a constant volumetric flow rate of V of T. Well, the head loss is simply the head loss through segment A plus the head loss through segment B. Very simple, nothing too complex there. But when we get into parallel piping systems, we have a few dynamics that we have to remember here. So again, we have a volumetric flow rate, V of T, that flows through, that comes in and leaves the system. Again, this is very similar to most hot water return systems. The volumetric flow rate of V of T is equal to the volume of water flowing through A plus the volume of water flowing through B. Again, we can't exceed the GPM going in and leaving the system. So each one, the two parallel branches have to, when you add them together, they have to equal the total. But this is the part that I've noticed a lot of engineers seem to struggle with. And that is the head loss through segment A has to equal in this system the head loss through B. And that the head loss from nodal point 1, where the system diverges, to nodal point 2, where the system converges, is also equal to that pressure loss of A through B. Now, there's a few ways we can have. Now, the next question I typically ask is, well, what is the volumetric flow rate of A versus B? And most engineers are able to say, well, and they understand it right off the bat, is, well, the volume flow rate through B is greater than A because that's the path of least resistance. Again, there's less of a pressure drop through B. The next question I ask is, how do you increase that pressure drop to get more? Well, I should say, I kind of gave away the answer there. But how do you get more water flowing through A? And it takes a little bit longer, but the answer is you increase the pressure drop through B. You could do that by making B longer loop. You could do that by reducing the size of B. And the most common methodology is, and the quickest answer, most engineers that get this question right, is you can add a balancing valve on B, restrict the flow. That creates an artificial pressure drop, if you will. So we take that same concept and writ large. We have a larger loop. Now we have 4 parallel branches. Again, nodal points are those points where the flow can diverge in a closed state condition. Also where pipe size changes, and also where you go from a supply side to a return side of the system. In order to get the flow from our water heater and recirculation pump in the mechanical room all the way out to our furthest point, assuming this is to scale, we have to add balancing valves to each one of those branches. Now, a lot of people say, well, you don't need assuming this is to scale, you don't need that D loop balancing valve. And that is technically correct. However, I typically see many engineers add this just in order to make sure they have more controllability of the system. That is, if there's another loop that gets added at a later date, they have a valve in there already rather than having to add it at a later point. Also, sometimes it's hard to determine what the most hydraulically remote loop is. It could be D, but let's say your pipe size in C, instead of being 1 inch, was ½ inch. You'd have to go back and forth and see which one was worse. And then if the contractor installs a system different than what has been shown on the diagrams because of construction conditions, now you've lost controllability. So again, having balancing valves on each one of the loops is generally engineering practice. In terms of valves, this is where we get a key note here is most of the industry has utilized manual balancing valves, such as this type is probably the most common way, where there's 2 integral readout ports and there's a control valve on the side. A lot of people think incorrectly that this is talking about GPM. It is talking about CV. As you can tell from the equation here, CV is indirectly proportional with the change in pressure through the valve, and it is directly proportional with the flow rate. Specific gravity we can ignore because it's 1 for water. So this is the part of the sort of the challenge. When these systems are not balanced, you can get a very you can get a lot of issues in terms of flow not going to where it should go in the system. When utilizing these valves, anytime the system is commissioned, there has to be balancing done on the system. And the balancing isn't just a once through. Every single time you have a change in pressure, you're trying to get a delta P, not a P. So that delta P, if we go back to our previous slide, is across each one of those valves. And so we have to determine what the artificial pressure drop is across each one of those valves. So often it requires the balancer to go back and forth between valves. The other challenge is if you add another loop to this system after the fact, years later, you have to go through and rebalance the entire system. This often does not occur on healthcare facilities as regulated as they are. And that causes massive issues in terms of potential for waterborne pathogen growth. What much of the industry is moving towards is automatic balancing valves, of which there are 3 types: pressure independent balancing valves, thermostatic balancing valves, and electronically actuated balancing valves. For pressure independent and thermostatic balancing valves, there's 2 types: fixed cartridge or adjustable types. Electronic offer the opportunity to do all the balancing electronically. And my sense is, if I was going to make a prediction based on trends I see in the industry, is I think, especially because of Legionella concerns and documentation reasons, many facilities in the healthcare world are going to start moving towards electronically actuated balancing valves. That said, the pressure independent thermostatic types could be another solution that many facilities will work. But I think from a documentation standpoint, my sense is that many of them will move towards electronically actuated balancing valves. So there's a number of considerations here, and I'm going to just use the last couple slides just to wrap up here some ideas in terms of things that will impact the hot water return system. One is pump selection. So the pump selection becomes key because, again, if we're building a hospital, one of the things that we should be aware of is the second the hospital opens, they're going to have a renovation project, and hospitals are never not undergoing construction or renovations or additions. So one of the trends I think that was also worthwhile seeing is that you're going to see many hot water return pumps switch from a constant speed type to a variable frequency drive, or ECM, electronically controlled motor. Now, I think there's a lot of debate within engineers, plumbing engineers right now, whether a VFD pump should be utilized in conjunction with the automatic balancing valves. In part, if you're sizing your system correctly, the pump should be running all the time. But I think there's an argument there to kind of overcome in terms of if the system is going between closed state and open state, that the pump can respond accordingly. But again, because of the parallel nature, my sense is that you're going to want to see 100% flow at all times. But the advantage of an ECM type motor is, let's say we selected a pump, that had 15 GPM and 15 feet of head, and we utilized this 3260 curve here. Well, you still have wiggle room as you increase the flow rate. You can get up to 20 GPM, roughly, maybe a little bit less, under that curve with that pump. And these ECM VFD type pumps, they have the ability to select a pressure and set point rather than swapping out the entire pump. This was a solution when I was on the engineering consulting side that we used to retrofit an existing hot water return system for a facility that was undergoing and having issues in terms of hot water delivery issues. Again, I mentioned the need for hot water balancing and commissioning. That is a requirement that is going to be needed for the facility. We also have right sizing hot water return systems. And utilizing in order to right size hot water return systems, utilizing the right supply pipe sizing can have a drastic impact on what your assumed BTU losses are through the hot water supply and return systems, which can shrink your hot water return pipes and pumps as well. Pressure drops and properly designing systems a big issue. I've noticed that high-rise engineers and healthcare engineers, when it comes to plumbing systems design, they have different experiences. And this is actually an error that I caught. Utilizing one hot water pump, or excuse me, one water heater to serve two pressure zones is okay, but you can't combine the hot water return systems into one. You need a reheat heater, which is a concept we see in high-rise design, where you have an express riser from your hot water generation system, and you loop downstream of the pressure reducing valve, and you have a reheat heater and recirculation pump in that system to account for the heat losses in that zone from multiple floors. In the previous case here, by combining two pressure zones, you had 80 pounds on hot water return pump 1, and you had 100 pounds on hot water return pump 2. In essence, you've created a dead leg in hot water return pump 1. And trying to do this through pump controls gets very, very tricky. And anytime you add complexity to a system, the likelihood for failure increases, which is why it's typically not recommended. When you look at some of the energy codes, actually the latest energy code in 2018, they added a requirement that the controls shall automatically turn off a pump when the water in the circulation loop is at the desired temperature and when there's no demand for hot water. In many cases, this was a requirement that was added due to bad design. And really, there's a lot of issues with this in terms of promoting the potential growth of Legionella in hot water return systems. And so this is one I hope we find exemptions for in the codes for exemptions for healthcare facilities and high-rise facilities and apartments and hotels and other hospitality, which is where we see most of the cases of Legionnaire's disease occurring, is in those complex hot water return systems. So when we look at our sort of diagram from before, again, getting automatic balancing valves that were still commissioned, to have a little bit better balancing there. A hot water return pump that's sized for future capacity, hot water supply based on the water demand calculator, an engineer that used Hardy-Cross methodology to size the pipes, and the future loop and hot water return pump were accounted for, and that they're properly located. These are all things that can fix those issues I mentioned at the beginning of my presentation. And so just to wrap things up here, a lot of people think that water is simple, but it's highly complicated. A great quote by David LaFrance, the CEO of American Waterworks Association. I've co-opted this a little bit. I think a lot of people think, in my experience, that plumbing is simple, but it is highly complicated. And this hot water return system, this is one that's been overlooked for decades. And really, we're seeing a lot of issues that come from this system being overlooked. My belief is that this calculation, the series of calculations, this design, especially for a larger building, can take up to a week. And that's what I experienced, especially when you're utilizing a program like Excel. This is one of those things that I think as an industry, we need to do a better job of appreciating and understanding and moving forward from. So just some key takeaways. Again, Hardy-Cross methodology is needed. We need to look at our whole system. Commissioning should be required, and balancing for non-automatic valves should be an absolute necessity. Paying attention to pressure zones is vital, and hot water systems design when they can balance energy and water safety concerns. And so if you're interested in contacting me, there's my email and my phone number. By all means, feel free to reach out. Also, if you're interested in hearing more, our podcast, the Authority Podcast, we cover a lot of these topics among others. That'll be a key conversation moving forward as well. So, and with that, thank you for your time.
Thank you, Christoph. Great presentation. We have one question, but I'm going to ask that we hold that till a bit later. I'd like to get Evan started pretty soon here. So can Evan join us, please? All right, Evan, it's your turn. And we have about 20, 25 minutes. I'll let you know in a little bit, but you just keep going for a bit, okay?
Hey, thanks, Gary. I'll go ahead and share my screen now. Can you hear me all right? And you're backstage, so I'll hope that you can, and drop it in the chat if I'm sitting here talking on mute. So what we're here to talk about today is why domestic hot water distribution heat loss matters. And before we dive into it, I'll go ahead and talk to you a little bit about why I'm the person here talking to you about it. And so if you've talked to me before more than about 20 minutes or so, you might find that I'm a little bit, some would say, borderline obsessed with commercial heat pump water heaters. And this obsession started when I started as an applications engineer at Colmac Water Heat. That's a heat pump water heater manufacturer based out of Eastern Washington, which is where I'm still located today, and where you'll see my wonderful background is that I get to look at all the time in real life. So as an applications engineer at Colmac Water Heat, I got to work with designers all across the country to figure out how to implement these heat pump water heating systems into their plumbing designs. And oftentimes the most difficult piece of information to get out of them was, what are the losses associated with your domestic hot water distribution loop or your temperature maintenance losses? So as a research engineer at Ecotope, I've been able to go beyond implementing just the heat pump water heater from Colmac. I get to work to implement heat pump water heaters across an entire initiative as part of the engineering firm at Ecotope that is focused on providing these leading edge solutions to decarbonize buildings. And that mission to decarbonize buildings from Ecotope aligns really well with my personal mission to be able to implement these green technologies to help divert this climate crisis that we're all experiencing. And some of the ways that Ecotope is doing this that I have been able to help with, especially in relation to heat pump water heaters, is we're trying to find ways. We're working with policymakers, we're working with manufacturers, and we're working with utilities to try and find the best way to implement these electric technologies, including heat pump water heaters, into modern day plumbing systems. And on the design side of our business, we've implemented over 75 heat pump water heating designs, and the temperature maintenance has been really important in making sure that those designs are sound. And then on the policy and innovation side, we've worked with these municipalities to try and implement tools for designers to use to make these systems reliable. And that includes sizing software and simulation software to figure out how much energy is being used. And both of these tools rely heavily on assumptions made by the hot water circulation system. So as a research engineer at Ecotope, I've been lucky enough to do a research study on the domestic hot water distribution system, which has been funded by Bonneville Power Administration. And today I'm going to talk a little bit about what I've learned. And the first thing that we're going to talk about is the actual definition of distribution heat loss and what I'm talking about when I throw these words out. And then after that, we're going to talk about how to measure it in existing buildings, because it's really important to see how buildings are performing, both from an energy perspective, as well as if we're going to retrofit existing buildings with energy efficient equipment like heat pump water heaters. And then we're going to talk about how to calculate the distribution heat loss in new designs, because we need to be able to size these systems really well in order to both decrease upfront cost as well as minimize the energy required to keep these systems hot. And then after that, we're going to talk about how to minimize the distribution heat loss in these systems. So first, defining distribution heat loss. And zooming way out on the domestic hot water distribution system, we're going to keep in mind our ultimate goal, which is to get hot water to the occupants when they need it. And we're going to make sure that we get it there hot. So the most chief thing we need to get hot water to the occupants is a functioning domestic hot water plant. And to be able to deliver this hot water from the plant to the fixtures, we're going to need a pipe for this hot water to travel through. And this is starting out really elementary, I know, but we're going to dive a little bit deeper as we go. So as this hot water is traveling to the fixture, it's going to cool the entire time it's going through this pipe, because the water is at about 120 degrees and our environment's a lot cooler. So naturally, we're going to have that heat loss no matter what we do. So in order to counteract this cooling of the water as it goes to the fixture, we're going to need to bump up the temperature that's leaving the heating plant. If we need 115 degrees at the fixture, we might need to serve it from the heating plant at 120. So it has that, so we can account for that heat loss as it travels to the fixture. So this works really well as long as this water is moving and it's actually being delivered to a fixture. But as soon as someone turns that fixture off or they're not in use, then this water is going to sit in the pipe and it's going to cool down even further. So then as soon as someone needs to turn on that fixture and access that hot water, they're going to have to flush all of that cooled water out of the pipe before they can actually have access to the hot water from the plant. So to counteract that, we're going to install this temperature maintenance loop that's going to continuously circulate water, so then we always have fresh hot water available whenever someone opens that tap. And because of these two functions that this heating plant's serving, we will have two forms of heat loss. We're going to have the delivery heat loss, which is the cooling of the water as it reaches the fixture. And then we're going to have this temperature maintenance heat loss, which is the cooling of the water that's continuously circulated throughout that loop and being returned back to the heating plant. So let's look at how these two types of heat loss and these two delivery flows interact. So our main goal, like I mentioned, is to get domestic hot water to the occupant and get it there hot. And in order to do that, we'll need to make sure that the water doesn't spend too much time in those pipes and cool down to a point where it's no longer acceptable from the occupant. And to do that, we'll have to make sure it's flowing quickly enough, meaning we have this minimum flow rate that we need to satisfy in order to maintain that hot water temperature. And just to make the numbers easy, we're going to assume that flow rate is 3 GPM. So if we're flowing 3 GPM to a specific fixture, that water will only cool down to, say, 115 degrees before it leaves the tap. And it's funny that I use this 30 BTU number after Christoph's presentation that I agree with as a standard of 30 BTUs per hour per foot of heat loss. But it does make the math really easy as we talk about this. So if we assume that we're losing 30 BTUs per hour per foot of pipe associated with this 3 GPM flow, we can then break that flow into this delivery flow, which is going to the fixtures, and then the temperature maintenance flow that's circulating through the entire loop and going back to the heating plant. And so if our fixtures are using 3 GPM, then we've satisfied our entire minimum flow rate requirement, and those fixtures are going to see 115 degrees Fahrenheit. If our delivery wanes down a little bit and we only see 2 GPM, now our water isn't flowing quickly enough to get to the tap in time, and it's going to overcool. So we need to provide just enough temperature maintenance flow to be able to increase that flow rate back up to 3 GPM so that water is flowing quickly enough so it doesn't overcool before it reaches that fixture. And since these two flows are mixing together in the same pipe, they're not sitting nicely as I've shown in this pipe here, but they're perfectly mixed together. They're going to be the same temperature throughout that entire pipe. And so maybe they're supplied at 120, but they're losing heat at the same rate. And so the heat loss associated with each of these flows is going to be proportional to the percentage of the pipe that each flow makes up. So if we assign some numbers to that, if we're flowing 2 GPM out to a fixture or a set of fixtures, and we need to accompany that with 1 GPM of temperature maintenance flow just to keep it flowing high enough, and we have 30 BTUs total, we're going to have this delivery heat loss of 20 BTUs and the temperature maintenance heat loss of 10 BTUs. So this 20 BTUs is what your heating plant is going to have to use to overheat the water so it doesn't overcool by the time it gets to the fixture. And this 10 BTUs is what your heating plant's going to have to reheat as part of the flow that returns back to the plant. And it actually is important to be able to talk about these flows differently, because again, I'll talk about heat pump water heaters because it's been at least 2 minutes. Because heat pump water heater systems can actually heat this delivery flow a lot more efficiently. They really like heating cold water up to a high temperature. But this temperature maintenance flow returns at maybe 110 degrees Fahrenheit, and heat pumps find a lot more difficulty in heating that warm water back up to a high storage temperature. So this temperature maintenance flow is actually reheated a little bit less efficiently in most of these really high efficiency water heating systems. So now that we've determined the difference between this temperature maintenance flow and this delivery flow and the heat losses associated with it, we can talk about how to measure these heat losses in an existing building. So if we have the proper monitoring equipment in this building, we can actually measure we'll start by talking about measuring the temperature maintenance heat loss. And so remember, that's the heat that's leaving this temperature maintenance loop as it circulates around. So using our basic heat equation, we're going to need to plug in a temperature differential as well as the overall flow from this temperature maintenance loop. So the temperature differential is going to be the difference between the temperature that's supplied from the mixing valve and the temperature that's returning to the heating plant. And then the flow, we can capture the overall flow returning to the heating plant, because we might have a lot of different branches coming off. I have a simplified loop drawn here, but we might have several branches, but they all come back together before they enter that heating plant in most cases, in a typical case. You'll just need to make sure you capture the flow before it splits back off into the cold water line that typically goes through the mixing valve. And so once we have that flow and that differential temperature, we can calculate the total BTUs lost by using this equation, 8.3 times gallons per hour of total temperature maintenance flow, times that temperature difference between supply and return. And one thing we've noticed after we've gathered temperature maintenance data on several different buildings is we've actually gotten short points of time where we're measuring negative temperature maintenance losses. And we know that there's no one in the building with a blowtorch up to these pipes or anything, or shoving heat back in these pipes. But what we realized is sometimes this thermostatic mixing valve isn't supplying a really constant supply temperature. So if we see this supply temperature spike, for instance, then we're going to see a spike in water temperature right here. But this water that has spiked in temperature hasn't made it all the way around the loop yet. So if we measure the return temperature at the same time, we're going to see a really big temperature differential, which is going to result in a really high BTU per hour reading. And the other way around, if this mixing valve temperature drops really quickly, then we're still reading this high return temperature because it takes a while for this water to get all the way around the loop. So maybe your mixing valve drops from 125 to 120, and now your return temperature at that same moment is still 122. Now our temperature differential is negative. So we're basically saying that this water is heating up by the time it gets to the return, which we know is not happening, but we need to make sure to account for that and not just take instantaneous readings in these buildings. We need to take readings over a longer period of time and then average those readings out to make sure we're accounting for those variations in mixing valve temperatures. So that was the temperature maintenance heat loss, and we're going to measure the delivery heat loss in sort of a similar way, but there are more assumptions attached to this delivery heat loss. So we still need a total flow that's being delivered as well as a temperature differential to plug into this equation. But the temperature that is a little tricky to get sometimes is this usage temperature. And if we wanted to be really accurate about the temperature, about the delivery heat loss from every fixture, we would have to measure the temperature and flow at every individual fixture and then calculate the BTUs out of each fixture. And usually that's not realistic in a monitoring capacity. So what we're going to do is we have to assume what this usage temperature will be. And a high level assumption can be this usage temperature is about halfway between the supply temperature and the return temperature. And the greater the difference you have between supply and return, the greater your error might be in making this assumption. So in order to calculate these heat losses in a design that hasn't been built yet, we can't put monitoring equipment on the pipes because they're not there and we don't have hot water flowing yet. But what we can do is we can look at the design drawings themselves and pull some necessary data to calculate these heat losses. So the first thing we'll need to know is the pipe size and the pipe length, because we need the overall surface area that heat is being transferred through. And Christoph mentioned that it's just heat leaving this water and transferring through the pipe wall and the insulation into the surrounding environment. So we'll also need that temperature differential that's driving that heat loss. And that's going to be the difference between the temperature inside the pipe, being the water temperature, and the temperature of the environment that pipe's in, whether it's in a parking garage or outside the building for some reason, or if it's in conditioned space. And we'll also need to know the insulation thickness and quality, which is usually pretty easy to gather because it's going to be code required in the jurisdiction that you're designing around. So you should know the insulation thickness and the conductivity of that insulation. And the more difficult thing to gather is how continuous this insulation is in a building. Right? There's certain things where there's certain places where contractors don't have to insulate continuously, going through joists as well as going through headers between each floor. So we have to account for the loss of insulation in some of these systems. So in order for you to not have to run the heat loss calcs for every section of pipe, because it does change as the pipe changes in size, I've created this calculator that is actually a lot like Christoph's calculator that I'm happy to report we get the same answer when we're plugging in different pipe lengths and sizes. But I created this calculator for BPA that has very simple inputs and makes some assumptions to be able to calculate this overall heat loss. So some of the inputs we'll need to make are the temperature of the conditioned space, which is about 70 degrees to make people comfortable, and the supply temperature, which is the water temp leaving the mixing valve, and then the usage temperature, which is the temperature leaving the tap. And then you can see we have this UA multiplier, which is basically a factor we're multiplying the heat loss by this factor to account for all of those imperfections in pipe installation. So everywhere that there's not insulation and anywhere that the installer's actual pipe routing might deviate from the perfect drawing you have on the design. And we also input the number of apartments. And what this is going to tell us is it's going to basically tell us how efficient our design is in terms of how much surface area and how much heat loss we can expect per apartment. So we can see the last thing we'll input here is, and this is a big one, of course, and this is where you're going to have the most lift, is we're going to tally up all the pipe lengths of different pipe sizes, and we'll input those in total feet of pipe of each pipe size. And then the calculator will pair each pipe size with a certain insulation thickness, and it will calculate how much heat loss you have throughout the entire system based off this average temperature throughout the distribution loop, as well as the overall surface area of your pipe system and the thickness of insulation associated with each size of pipe. And it looks like we might have a question, Gary.
We do, but I want to wait. You need to finish up. We've got 10 minutes, less than 10 minutes to the end of the presentation. So go for it, dude.
Okay, great. So what we'll get as an output from this calculator is going to be the total heat loss in the entire loop and the watts per apartment heat loss, which I like to reference watts per apartment because our EcoSizer tool that sizes heat pump water heating systems accounts for, it has a watts per apartment input for recirc losses that we're assuming, and that is the standard watts per apartment assumption in that sizer is 100 watts per apartment with a 1.5 safety factor. So it's a pretty conservative heat loss. So then we make sure we don't undersize that temperature maintenance heater. There we go. So now we've talked about we've defined heat loss. We've talked about how to measure it in an existing building, and we've talked about how to calculate it from your designs using this simplified calculator that I should have mentioned uses the same equations that Christoph mentioned in his first presentation. So now we're going to talk about how to minimize this heat loss. And first we'll talk about why it's important to minimize this heat loss. And to do that, let's look at the energy usage in a typical baseline multifamily building. And from this pie chart, you can see that about a quarter of the heat provided, or a quarter of the energy provided to a typical multifamily building, is accounted for by domestic hot water heating. And within that 25% of energy usage for domestic water heating, 10%, or almost half the water heating load, goes towards this temperature maintenance loop. So that is almost half the energy going into the system that isn't actually used by the occupants. So we want to find the best ways to minimize this temperature maintenance loss, as well as the delivery heat loss that's baked into this primary heating percentage. So if we think about this in terms of applying heat pump water heaters as a way to decarbonize our buildings, we have to think about how these are sized and how it affects these systems, and why this has been such an important issue for me since the beginning. And we have to keep in mind, if we're sizing a typical gas water heating system, usually that system is sized to handle the all-time worst peak hot water usage, probably a peak hourly usage that building will see. So these gas water heating systems are sized with a really high capacity and this small, consistent temperature maintenance load relative to that giant all-time peak water usage is pretty small. But the way we size heat pump water heaters is we basically look at them like trickle chargers that charge this hot water storage. And the hot water storage is what satisfies those peak loads, while the heat pumps run 16 to 20 hours a day to satisfy this average hourly usage that makes up the total daily usage. So these heat pumps are slowly humming along, recharging these tanks. And then if we drop in a temperature maintenance load or delivery heat loss that almost accounts for half of the overall heating load, now we have to upsize these heat pumps by about 50% to be able to accommodate those loads. So recovery is not cheap with heat pump water heaters, so that's going to add a lot of capital cost, as well as add a lot of energy usage to your building. So we need to decrease these losses so then we can decrease these system sizes as well as the energy usage, which in turn will decrease the carbon emissions from our buildings. So the way we're going to minimize these heat losses, and the first way is going to be to minimize the surface area of the pipe. And the surface area is accounted for in two ways. It's going to be the diameter of the pipe, or which drives the circumference of the pipe, as well as the length of the pipe. So in order to decrease the diameter of the pipe, we're going to need to size these pipes properly, the peak flow that they will see throughout the life of the building. And currently, most municipalities or most jurisdictions will refer to the Hunter's curve, which was created back in about 1940, which is a really long time ago when fixtures were a lot different. So the sizing term, the way that we can size systems has been updated and formed much better in a way through Appendix M, which Gary Klein has actually been a very vocal proponent for and can tell you a lot more about Appendix M in our later conversations. But it is a great way to size the pipes much smaller to account for peak water flows that are actually realistic for today's fixtures. And if we're sizing for smaller flows, we're going to be sizing these pipes much smaller, which means a smaller surface area. And the other way that we're going to minimize surface area of these pipes is through thoughtful design and thoughtful routing of our pipes. So if you look at these pictures of two buildings on the right here, you can see they're the same buildings with the same number of units in them, but the building up top here has a lot more hot water risers. So you can see the water travels from the water heater and up these risers and then back to the return line, which returns back to the water heater. So a pretty typical design. But if you were able to work early on with the architect and thoughtfully plan your pipes, you could arrange these units and the pipes that serve them to allow one pipe to serve 2 units. So we're cutting the number of risers we have in half, which is going to greatly reduce the amount of surface area that serves as a means of heat transfer out of the hot water in these pipes.
1 minute.
Great. And the other thing we'll talk about is minimizing the water temp. So we want to decrease the supply temp as much as possible while still supplying the occupants with the proper water temperature. And the best way to do this is through branch balancing. And Christoph mentioned these thermostatic balancing valves, which I think are a great way to do this, to provide just enough temperature maintenance flow in each branch to be able to satisfy these water temperatures. And then the timed recirculation pumps are a way to create less heat loss in a system. You just need to make sure that they're applied to the proper systems for the same reasons that Christoph mentioned in his last presentation. We don't want stagnant water in these pipes. And we also want to make sure that as soon as someone turns on a tap, they're going to get instant access to this hot water. So a good application for timed recirc pumps might be an office building when we know there's not going to be occupants in that building from X time to Y time. And the last thing that we're going to need to make sure that we do is have proper commissioning in our systems. So this will do a couple things. It'll make sure that the installers are installing these systems as we intended as a designer. And I'm speaking as a designer, but I could be speaking to installers as well. And the second thing that's really important is we need to be able to learn from these installers and hear the challenges that they went through to install our designs as designers. Because if we make our future designs a lot more amenable to the actual challenges in these buildings, then we're going to have a lot better chance of installers following our designs as we intended if we're actually listening to the problems that they're facing time after time as they try to install these designs. So my mission at Ecotope has been to lower carbon emissions in buildings and lower energy use, as well as lower the cost of water heating. So I think I've been able to accomplish that at a lot higher value after doing this research study and learning what I have. And I hope I've been able to share with you today some points that will will help you do the same.
Evan, thank you so much. Christoph as well. I want to thank our speakers for today's session. I think we did a great job. And I have a few questions to ask you myself, but we have 4 or 5 questions from the audience. Thanks to our attendees for participating. If you'd like to continue, please follow us on the Zoom chat room, and the link can be found on your website. So with that, I'm going to end this session and head over to the other one. And see you in Zoom in a few minutes. Bye now.